Okay, so I guess we're going to get started. It's my pleasure to introduce Brian. We're going to talk today on complexity and support varieties for type P, these superalgebras. Thanks very much. I hope everyone can hear me. If not, you try turning up your volume. Anyway, this is a talk that I was supposed to give the Monday after spring break last year. And needless to say, that did not happen. And so I'm glad to have the opportunity to reschedule it today. The work I'm going to talk about is all joint with Jon Kujawa. And it's going up here in Math Research Letters. And everything is over C. And so let me tell you the setup. G is going to be a least superalgebra of type Pn. It's a set of 2n by 2n complex matrices in block diagonal form, not block diagonal, but block form, where B is symmetric, C is antisymmetric. And this is a subalgebra of the superalgebra GLNN that Dan defined 3 weeks ago. So I'm hoping that that means you know that the even part, G0 bar, is this diagonal stuff, A minus A transpose. And the odd part is the off diagonal stuff, B and C. And I don't think Dan mentioned, but this actually has a compatible Z grading, G minus 1 plus G0 plus G1. G0 is the same as this G0. G1 is the B part, and G minus 1 is the C part. And this is an interesting setup because there's no transpose that interchanges G1 and G minus 1. They're different dimensions. G1 is bigger than G minus 1. And so I think that feature makes this one of the most interesting classical superalgebras in terms of its representation theory. It's what's called a type 1. This means that the compatible Z grading concentrated in degree plus or minus 1, 0. So let me define a couple of subalgebras. P plus or minus is going to be G0 plus either G1 or minus 1, respectively. H will be the diagonal matrices, which is sitting inside of G0. So it's just the usual Cartan setup for G0. I'll introduce the standard linear functionals on H. So just the diagonal coordinate of this. You can think of it as living on this A matrix here. This one's obtained from that. And then we'll be looking at the integer weights. So this is the sum. That's 1i. And sitting inside there are the dominant integer weights. X plus of p. So these are the mu, this is sum mu I epsilon I, where the entries are non-increasing. So the usual dominant integral weights for GLN. Okay. Rho here is the sum of n minus I epsilon I. Now, the category that we're going to study, F, is the full subcategory of G modules, satisfying 3 conditions. They're finite dimensional, they're H semi-simple, completely reducible, has modules for H, and the weights are all integrals. Even though these are finite dimensional representations, those of you that know things about superalgebras know that those categories can still be pretty interesting. They can be non-trivial extensions. It's not semi-simple. So let me tell you about some special interesting modules. Category. So we fix dominant integral weight mu. And let's let L0 of mu be the finite dimensional simple module for P0. P0 is just GLN, remember, of highest weight mu. We can induce this up. We take U of G, universal super enveloping algebra of G, tensored over U of P minus. That's the one. So we play this to a P minus module by letting G minus act by 0. Okay, and this is the usual kind of Fermat module construction. But in the super world, this is called a Katz module. And because Pn has these two different P minus and P plus that look pretty different, this one is called a thick Katz module. Maybe I'll just say parenthetically, although oops, there's supposed to be a mu here. Sorry. There are also Katz modules that are induced from U of P plus. And these are finite dimensional, by the way. This is finite dimensional because of the PVW theorem for superalgebras and the fact that the enveloping algebra on the superalgebra, which you can replace this by basically U of G minus 1 tensor over C of this thing. And U of G minus 1 is finite dimensional because G minus 1 is purely odd. And this is actually a module in the category. There are also thin Katz modules, which are similar, but using U of P plus. And so I might have just said the wrong thing. This should be like U of G plus 1 tensored over C of this thing, which is bigger than U of G minus 1, plus P plus 1 is bigger. So these are called thin Katz modules. And they're also finite dimensional, but smaller dimensional than these thick Katz ones. The usual kind of theory says that this guy is a highest weight module, and it has a unique simple quotient. Denoted L of mu. And the L of mu is as mu varies over L the dominant integral weights to form a complete irredundant set of simple modules for this category. I'm lying slightly, but you also have to take pairs of changes into account, but this is not very good pair. And the category F has enough projectives. So we can let P mu be the indecomposable projective cover of the simple module, which also, by the way, covers that thick Katz module, the highest weight module delta U. This is the indecomposable projective cover value. Okay, comments, questions? So let me tell you some more about weights. Well, maybe I'll say, first of all, the goal of the talk, or the main goal of the talk, is to construct projective resolution for these thick Katz modules. Okay. So we have the beginning of it, which is P mu, and that one, but we want to extend this to a whole projective resolution. So I need to say some things about weights and weight diagrams. So remember our mu epsilon. This is basically for the whole talk. This will be a fixed dominant weight. This is called typical. And the entries are all different. Otherwise, it's called atypical. And then lambda is another dominant integral weight. Then there's a partial ordering on this dominant weights. mu is less than or equal to lambda, if and only if, somewhat paradoxically, lambda I is less than or equal to mu I for all I. That's a little bit confusing, but that turns out to be the right definition. And if you have two such weights ordered like that, you can define their relative length. L lambda mu is the sum of the differences mu I minus lambda I. This is an important metric. And now if I write mu plus rho, sort of with entries in reverse order. So I want to write this as an epsilon 1 plus a1 epsilon n. If you remember rho is like n minus 1, n minus 2 down to 0. If you add that on to a weight that has non-increasing entries, they're going to be strictly decreasing. And so a1 is strictly less than a2 less than an.
Is there something you call that a length rather than like a height or something like that?
This following comes on the
Because I was wondering if you think of like something like that,
maybe I'll repeat the question. Bill was asking me if there's a reason why it's called a length rather than a height, and if it's somehow connected to an affine buffer. I don't think it's connected to an affine buffer at all. And so I'll write square brackets mu for this sequence of and I'll depict it on a number line by just putting a dot at each of these entries, going from left to right, and then moving ticks at places that don't have dots. And this is called the weight diagram of mu. So let me do an example. So let's say, so here's an example. Equals 4, and I take mu to be 3 epsilon 1 plus 2 epsilon 2 plus 2 epsilon 3 plus epsilon 4. Remember, rho is like 3210. So you add rho, you get mu plus rho is 6 epsilon 1 plus 4 epsilon 2 plus 3 epsilon 3. So this mu diagram has a dot at 1, 3, 4, 6. So that's the weight diagram. And notice that this mu is atypical because these two entries are the same. And that corresponds to these two dots being adjacent. So that's how you can tell if the weight is typical or not. In the weight diagram, you'll have at least two adjacent dots. Okay, so the most important tool that we used in constructing this projective resolution that we're working towards is some translation functors. And these were worked out by a group called WinArt, which stands for Women in Non-Commutative Algebra and Representation Theory. They started off at a conference in Banff in 2016, and they ended up writing a 10-author paper, starting with Balagovich and ending with Sarganova and Strobel. And it was published in 2019, also in Math Research Letters. So what they did in this paper is that for an integer I, they defined a translation functor, so capital beta I. It's the functor from F to itself, and it's exact. It's defined by first tensoring a model with the natural representation for Pn, and then projecting onto the generalized I-value space of a certain passenger type element that they construct. So it's kind of a standard type of thing to try to do. And they computed the effect of this functor on most of the models that are floating around. In particular, the thick cats modules that we're interested in, they did the thin cats modules, and they did the indecomposable projectives. And let me tell you a couple of facts. So the first fact is that theta I of a, for some reason I'm switching to lambda. Theta I of an indecomposable projective is either some other indecomposable projective or zero. That's it. So in particular, it takes projectives. And the second thing that I'm going to need is some cases of what it does to a thick cats module. So there's several cases, but the only two that we ended up needing were these two. It's defined in terms of weight diagrams. So if the weight diagram of lambda has a dot at I minus 2, but not at I minus 1 or I, then beta I, this guy, of delta lambda is equal to a delta mu, where mu is the thing that you get by moving this dot one space to the right. And this is a local definition, so all the other dots in lambda are unchanged in mu. Okay? So just locally, it has to look like this, at these three spots, and then you get this guy. So the second case, if lambda has a dot at I minus 2, nothing at I minus 1, and another dot at I, then there's a short exact sequence. So beta I of lambda fits in at the middle, and this is going to project onto a certain delta mu that I'll tell you in a minute, and as a submodule of delta mu prime. So before I tell you what these weights are, several of you are probably familiar with this kind of situation. It comes up in category O for a simple algebra or C, where you do translation functors off the wall and get some short exact sequences like this. And it also shows up for characteristic P representations of the groups, where you do translation functors for induced modules. So this is kind of a familiar thing. And let's see, maybe I can fit these in down here. Sorry if I can. So mu, the head of that guy, is this fella, where you move the dot one to the right, and mu prime, the submodule, is the one where you move the I over to the left. Okay, so you're sort of trying to move this dot over to the right, and that would be good. That's what we did here. We moved this dot to the right. But this time we have this sort of extra thing that's this guy over here. Anyway, as I say, there's a bunch of other cases, and sometimes it's zero, but these are the only ones that we actually need. So with that preparation, here's the algorithm. So the goal is to construct a projective resolution, which I'll call P star of mu. This thick cats module. Use some fixed confidence probability all the time. And we sort of borrowed an idea of John Brundon. We did this for the cats modules for GLMN in a paper in 2003. So the starting point is the observation that I made a little while ago, that mu is typical. Then, well, maybe I didn't say this. Delta mu is actually equal to P mu. The typical thick cats modules are indecomposable projectives. And And so we have a trivial projective resolution. Just take P of u, and then 0 is the general one. And this is just the identity map. P of u is equal to delta. So this is degree 0, degree 1, degree 2. That's the projective resolution of delta u. And so then the key to the algorithm is to find a sequence of ways starting from mu, with mu is atypical, and going to something mu 0 that's typical. And I'll show you an example. So we found a very specific sequence of dominant integral ways starting mu and ending at some mu 0, which is typical. And each one of these steps corresponds to one of these translation functors. And so you can start at the other end, start at the bottom on mu 0, with this being the projective resolution, and then just apply translation functors. They're exact, they take projectives, so they're going to give us projective sequences. So let me just show you an example of how this works. So let's take a mu to be 2, 3, 5, 6. And so 2, 3, 5, 6. The procedure is to, starting at the dots at the left, move dots to the left, one step at a time, until there's no dots adjacent to each other anymore, which is what typical means, right? Typical should have not any adjacent dots. So these pairs of adjacent dots are a problem. So we want to move things to the left, but there's one caveat. You're never allowed to move the dot to the left so that it occupies the space immediately to the right of some other existing dot. Okay, so here's what we do. This 2 dot first has to go over here. 2, 1, 1, 3, 5, 6. And now I've separated these two, which is good, but I would like to next move this 5, but I can't move them here because that will put them next to this 3, and that's sort of counterproductive. So I actually have to move these guys farther. So I need to move this guy from 1 to 0. Now I can move the 3 over. I see I'm going to run out of room. I should just punch. 0, 2, 3, 4, 5, 6. Now I can move the 5 over. So this is mu 0. And I number backwards, so that's mu 1, mu 2, mu 3, 4. This is my original mu. And now there's some translation functors that take me from one to the next. This guy here involves moving 4 to 5, and that's a theta 6. Remember the dot gets moved at I minus 2. So that's a theta 6. And then we have 2 moved over to 3, so that should be a theta 4. Here, 0 moved to 1, so that's a theta 2. 1 moved to 2, that's theta 3. So I have a projected resolution already for mu 0, and I can get roughly, I'm not going to be too precise, but roughly we use induction on how close the weight is to typical, according to the scheme. So mu 3 is closer to typical than mu 4 is, because it takes fewer steps. And so we start at the bottom and work our way up, and there are 2 things that can happen. Now, let me. Not really. I don't think this distance from typical is not what we're going to propose as the totality of what. I mean, it's a measure of something, yeah, but it's not not the result. Yeah. Okay, so these two steps in the middle are actually the easiest because in this step from here to here, what happens? 2 and 3, and there's nothing in this spot either. I actually looked here. 2 is going to move over to 3. There's nothing in that spot. And that's the case where case 1 of the translation function applied to delta. And the same thing over here. This step here takes 0 over to 1, and this space is also empty. So let me just maybe show you one of these. So the 2 middle steps are easy. So let's say, for example, if we have P U1, the delta U1 already. And here, let's say I have this one somehow. I haven't told you how to do that yet, but I will. And then you can just apply theta 4. And you get theta 4 of P U1. It's exact. So we get a resolution of theta 4 delta U1. But according to that rule number 1, this is equal to delta U2. Because these two guys are empty. And these guys are projective. You know, this is a dot or a star or something like that. Each one of these in each degree is some direct sum of indecomposable projectives that, let's say, we already know somehow. Then you know that by applying the rules from the Winard paper, every one of those indecomposable summands goes to either some other indecomposable summand or 0. And so it can be to figure out what this is. And it's going to be some projective thing. And it's exactly that. So that's the easy case. I want to show you the harder case. Probably in general, I wouldn't do this, but I advertised this talk in my homological algebra class. And we're actually going to use 2 key theorems from Weibel's chapter 2 of homological algebra. But I thought it would be kind of fun for the students to see how this actually works. So let me show you this top step. And the bottom one is more or less the same. Just to simplify the notation a little bit, let me call this guy here U. So here's the top step. So remember, I get a shorting back sequence. Theta 3, I guess I'm applying. Mu is this guy here. I'm trying to move a dot over one place, and I get this as one of the guys. This is the guy mu that's in the head of this middle term. And then the other guy, mu prime. Matters too much, but mu prime is like one over. So it's 1, 2, 5, 6. Anyway, it doesn't matter too much. So I'm going to erase all this so I can show you. So we can take the projective resolution of delta nu that we already have by induction. And so let me write some of that down. Here's P2. And I can apply theta 3 to everything. This, so exact. And this goes on. What is theta 3 of delta nu? It looks like delta mu sitting on top of delta mu prime. I could write it like that. As a filtration, a 2-step filtration where the bottom modulus delta mu prime and the quotient of the top by the middle by the filtration terms. one thick cast module on top of another. So delta mu prime embeds into here. Some conclusion I. Just sitting in the bottom. This one. So, now I have a projective resolution of this guy also. So here's P0 mu prime. The comparison theorem in homological algebra says that you can extend this mapping to a chain map like this. I0, I1. So that's the comparison theorem. Because this is a projective resolution, these maps kind of extend because of the property of these projectors. So that's in Weigel chapter 2. And now what I have is, you can think of this as a double complex. It's only 2 rows, but it's an upper half plane double complex with exact rows and something called the acyclic assembly lemma. It's also in Weigel chapter 2. Tells you that the total direct sum complex of this is still an exact sequence. So we take the direct sum going along these diagonals, sums, we get something. So it has 0 here, it's going to have theta 3 delta mu there, it's going to have something like theta 3 P0 here plus delta mu prime here. So in the direct sums as you go along. So this is still exact. Now we're pretty close. Remember, theta 3 of delta mu is this guy. And it has delta mu prime sitting in at the bottom. So let's do that again. This embeds in here. This guy obviously has a delta mu prime sitting in here as a direct summand. This thing is a subcomplex of that one. And if you take the quotient complex, you get what you want. You take the quotient complex at the end here, we get just this top, delta mu, right? This thing goes away, and we just get theta 3 of P naught of mu, and then the other terms are things like theta 3 of P1 of mu plus P naught of mu, and so on. So the quotient complex is a better resolution of this top in here. So that's pretty cool to be able to use these two basic homological algebra results to produce projective resolution. So that's the algorithm. Questions, comments? Okay. So, all right, now we have a projective resolution of some interesting modules, these thick class modules. What do we want to do with it? Well, I suppose if you're in the John Carlson School of Representation Theory, you should try to figure out what is the rate of growth, the dimensions of the terms in your projective resolution. And in order to do that, you basically need to know 2 things. So let's say, what's the rate of growth? I'll say a bit more about what this really means if you don't already know. So let's say the dimensions of P. So you need to have some control on what summands can be in there. What possible indecomposable summands can be in this, could be term of this. And then you also need to know like how many summands, indecomposable summands are in there. Well, if turns out that a small miracle occurred, and this, I think, is partly explaining the particular choice of sequence of weights that we chose. It turns out that when we're doing the algorithm, none of the theta I p lambdas vanish. So it turns out, so I don't know, I don't have too much left. You know, we have two cases, and we took something like theta j of a p nu, let's say, is one of the steps in the algorithm. In both cases, we have to do something like this. So let's say p d nu. So in this, none of the summands, the indecomposable projective summands, are killed. Remember the Winnar paper said indecomposable projective can either go to some other indecomposable projective of 0. We're able to get enough control of the summands that were in here to see that none of them are in that case we can go to 0. And so we know exactly how many summands there are in each case. You type in the first easy step, you know, you have the same number of summands as you did before. If you just apply theta to the resolution you had before, you got the new one. In the second case, where we do this basic assembly line, it's not much worse because we're applying theta on the first row, and then we're just sort of adding in the term from the second row. So the degree d term gets a theta applied to the degree d minus 1 term on the other one gets added in. And so the number of summands is just the sum of the two number of summands. So you can write down, in fact, a recursive formula for the number of summands, and it's very straightforward. I'll try to tell you more about that before the end. But here's where I'm going to try to tell you about this other step. What weights lambda are such that p lambda occurs in here? Because we need to know what the dimensions of these things are. And if we have some control over how sort of spread out the weights are, we can use the biodimension formula. So this, let's see if I can put this back on. Put this down. Start sharing. Now, so we figured out a formula for what these guys are, a combinatorial formula. And I'm going to show you how it works by this app that I wrote for the iPhone and iPad. So let's say we start, these circles represent a number line with ticks on them, more or less. And I can make dots. So the top row is a weight view, which has weight diagram 7, 9, 11. And the bottom row represents the weight lambda. It's going to vary. They're both going to vary as we go along. And these vertical lines you should think of some sort of a projection from the top row to the bottom row. And now there are 3 moves that start from something like this, which is typical, and produce new pictures like this. So here's move 1. I don't know, you can't tell what I'm doing, but I'm just tapping. I'm tapping on the dials. So that was move 1. You can move a pair of dots connected by a straight line, one place to the right, as long as both right positions are empty. Now I can't do that anymore, but here's move 3. I can take those 2 dots in the top row, and I can move them over one, leaving the bottom row the same. And I'm going to do that again. That's move 3. And here's move 1 again. So I've moved that guy over 1. I can do move 1 to him again. But now there's a problem. The top space at 10 is empty, but the bottom space is occupied. So when I move that guy over again, watch what happens. The bottom guy gets bumped over 2 spaces to the left. And I can do that again. And so let's just stop there. I've shown you the 3 moves. And so now let me start sharing a different screen, which is where. Okay. So can everyone see the screen at home that I'm sharing? I hope. Let's assume yes. So the picture that I just showed you, I'm going to view it as a bijection F from the top row to the bottom row. And those are weight diagrams of some weights mu and lambda. And the definition of an allowable function F from mu to lambda is something like that, which can be obtained from the identity function from a typical weight to itself. So typical, remember, no pairs of adjacent dots, by applying a finite sequence of those three moves, 1, 2, 3. And then if F is such a function, and the top weight has coordinates A1, A2, up to AN, then we assign this integer L of F to F, which is the number of I less than J, such that F of AI, and remember, I less than J means AI is less than AJ, because the A's are in increasing order. F of AI is greater than F of AJ. So if this was a permutation, this would be that's not the right word. Inverted thing. These are like inversions on permutation, except that the top row and the bottom row don't have to be the same. But if I go back to my picture here, this thing has two inversions, or we actually call them leapfrogs, so I can't draw this out. But there's two pairs, I guess 11 and 12. Oh, no, I shouldn't call it that. The first and the second dots get swapped when you go from the top row to the bottom. And so do the first and the third dots get swapped. But the first dot is to the left of the second dot in the top row, of course. But the first dot moves somewhere to the right of where the second dot goes in the bottom row. Sorry, I can't draw this out. But the first dot is going to 11. And the second dot is going from 12 over to 8. There's two inversions in this one, and they correspond to the two crossings that you can see in the picture. Okay, so they're just basically crossings in the picture. And we originally called these things leapfrogs. We drew them in a kind of different way. So the L of F stands for the number of leapfrogs. And here's the theorem. So mu is going to be always a fixed element integral weight. Then there's a bijection between these allowable functions from mu to lambda and summands P lambda of this projective resolution of delta mu that we constructed, P star of mu. And under the bijection, moreover, P lambda occurs as a direct summand in degree D of the projective resolution, where D is 1/2 the relative length function L of lambda mu minus the number of leapfrogs. So this theorem really took us a long time to figure out. It's super easy to prove. It's basically just a matter of following along what the theta i's do to the projectives that occur in the resolution. Once you have this formula for what they should be, you can apply the inductive process in the algorithm, and you can easily see that this is the right thing. Those moves 1, 2, and 3 come from the two cases of how you put these things together. So it was very frustrating that it took us so long to figure this out, but it was so easy to prove. Well, I just want to give you maybe one more example on the app of kind of the phenomenon that can happen. And now I'll switch to some examples on the PDF file. So let's start with 9 and 7 and apply move 1, and then we'll do move 3 twice. And then let's fill in a 6 and a 4. So I'm cheating a little bit because I'm really supposed to put in all these dots at the beginning for a typical way to move things, but pretend that I had done that at the beginning and these are maybe moved over as they need to be. Let's do a move 1, a move 2, a move 2, another move 1, a move 2, a move 2, and a move 2. And so here, can you see the top of the screen? You can't see it at all. Up arrow on the screen. Oh, good. Thanks. Well, the little recording thing is over top of something, but that says the rank is 4. That's there are 4 dots in each row. The n is the number of dots, remember. The length is 12, so if you work out that length formula difference that I said, remember you say GI minus lambda I for all these possible pairs. You get 12. The number of leaps is 4 crossings. And so this corresponds to an occurrence of that L lambda 4, 5, 8, 9 in delta mu 8, 9, 10, 11 in degree 2, the top right number there. That's 1/2 of 12 is 6 minus 4 is 2. Okay. Let me reset this. Try to remember that if you can, but I'll show you in a minute. Another one that I can do is starting up similarly. And I'm going to go 5, 3, and push that 3 over to 4, and then I'm going to do a bunch of move 3s. And now, if you were paying attention, I have the same pair of weights. I still have the length difference of 12, of course. Now I have no leaps, there's no crossings in the lines going from u down to lambda. And so this is an occurrence of the same p lambda in degree 12 over 2, 6 minus 0, 6. So let me go back to the PDF and I'll show you. There's that example that I just showed you. And so you have the same indecomposable p lambda occurring in degree 2 and in degree 6 of the projective resolution of this particular delta U. That's pretty common, having the same projective indecomposable in 2 different degrees that differ by a multiple of 4. We discovered. Okay, now the next example, I'm just going to put these 2 pictures together in kind of separated from each other in 2 possible ways. So here's 2 copies of those pictures, kind of separated enough, but with the order of the 2 pictures switched. So now I have a pair of weights, lambda and mu, that are the same in both pictures. The length difference is 24, and both functions now have 4 leapfrogs, 4 crossings in both of them. So these pictures correspond in my projection to 2 occurrences of the same p lambda in the same degree 8, that's 24 over 2 minus 4. You can have the same indecomposable occurring more than once in a particular t resolutions. Okay, that's not so bad, but now comes the bad news. This was a big surprise. Here we have the same pair of weights, mu and lambda, in both pictures. The length difference is 12. 12 over 2 is 6. The first has 2 leapfrogs or crossings. 6 minus 2 is 4. So that occurs in degree 4 in the first picture. The second picture only has 1 crossing, and so the degree is 5. So we have 2 occurrences of the same p lambda in 2 successive degrees in this resolution. Now, John Carlson was the first one to explain to us that if that never happens, if you have a projective resolution, and we never have the same indecomposable projected in 2 successive degrees, it's automatically minimal. Sadly, we have not been able to prove whether our projective resolutions are minimal or not because of this phenomenon. Yeah, so we don't know. Even for this example, we could not figure out whether this particular projective resolution is minimal. This degree is far enough out in degree 4 and degree 5 that it's really, really hard to figure out what the maps are all the way up from the bottom up to this point. So here's a possible problem for grad students. Try to prove that our resolutions are minimal or find a caveat. We don't know. I don't. So Dan said if you had a minimal projective resolution, you could use it to compute the x between the standard models and irreducibles, exactly, and that would give you the causalist polynomials. And And if this was a minimal predictive resolution, then parity vanishing fails for the listed polynomials. And that's a very, very, very interesting thing that might happen. I should say, this category F is a highest weight category. The deltas are the standard modules, and the nodules are the co-standard modules. There's no duality, swapping one for the other. And we don't know if it has a listed theory or not in the sense of one partial stuff. And it's all intimately tied up with what Dan was just saying about if these were projective, minimal projective resolutions, then you would not have parity vanishing for listed polynomials. Basically, they wouldn't be polynomials of Q. They'd be polynomials of Q half. And that's how it works. So yeah, very good question. I think I have maybe about.
I have one question. I think you're looking at I assume you have a filtration.
They have filtrations by deltas and nodules.
But whatever is closer to being projected.
Yeah, the deltas are close to projected.
Do we actually know how many other filtration factors we have?
Well, the Winard paper worked that out. The Winard paper worked out what the nodule filtrations are, or the delta filtrations are for speeds. It's a complicated combinatoric process involving weight diagrams and arc diagrams with problems underneath them. There is a formula for it, but it's kind of like, I don't know, inverse scattering problem or something like that. You have to find all the ways that have a certain property when you follow some arcs and diagrams. Anyway, those are known. Those filtrations are known, and the Winard paper also figured out the composition factors of the deltas and of the nodules. So those are known, I guess, by PGG reciprocity or Frobenius reciprocity. Right.
Yeah, I guess I don't know. The first times that we use the actually
Then it said the first occurrence of an asymmetric decomposition occurred in the state of thesis and still had reciprocity. So, yeah. Well, let me just maybe quickly show you some theorems. So I mentioned the rate of growth. So here's a definition of the rate of growth of a sequence of integers. It's the smallest positive or non-negative integer c such that the sequence A sub b is less than or equal to a monomial in d of degree c minus 1. And if there's no such c, then you say the rate of growth is infinity. The complexity of a module is the rate of growth of the dimensions of a minimal projective resolution. And in the Jon Kujawa and Nakano papers, we introduced this other notion of the complexity of a module, which is the rate of growth of the number of indecomposable summands in a minimal projective resolution. And that's another interesting invariant of a module. Actually, in some ways, a better invariant because it survives as a categorical equivalences. Anyway, let's introduce this notation. C mu is the rate of growth of the dimensions of PV of mu for this specific resolution that we constructed. Okay, so we don't know that this is C of delta mu because we don't know it's minimal. This is an upper bound at least. S sub d of mu is the number of indecomposable summands of PV of mu, and Z of mu is the rate of growth of SD of mu. So because of the small miracle that I mentioned before, we have an explicit recursion formula for these SD of mu's in terms of SD minus 1 and SD minus 2 or something else. And the key invariant that seems to be showing up here is these runs of mu. So a run in mu is a maximal sequence of adjacent dots in the weight diagram. And the size of a run is the number of dots it contains, and the parity is the parity of the number of dots. And we write pi or pi of mu for the sizes of the runs of mu, which will be a composition of n because they're n dots. So this example here has a run of 2, a run of 1, and a run of 3. So the pi is 2, 1, 3. And we let O or O of mu be the number of odd runs of mu, runs of odd size. This has 2 odd runs. And if you're bored and want to do a little homework problem, you can prove that n minus O is always even. Here's the generating function for those number of summands, SD of mu. So take this generating function. Turns out it only depends on the composition, this pi of mu thing. So I write S sub pi of q sometimes. And if pi is just a single number, n, in other words, mu is a single run, then I'll write S sub n of q. Here's some formulas basically for that. S pi of q is the product over the parts of pi of S pi j of q. So in fact, it doesn't just depend on the composition, it only depends on the associated partition of n. Doesn't matter what order they're in. If you just have a single run, so Sn of q is some polynomial Fn of q divided by 1 minus q to the 4 of n over 2. And the Fn is some polynomial given by an explicit recursion formula, we could solve that. If we solved it. Didn't need it, but we did. Putting those two together, then the S pi of q is just F pi of q in the numerator, which is the product of the F pi I for the various parts, divided by 1 minus q to the n minus o over 2. And then just using a little standard Taylor series theory, that means that the rate of growth of these numbers, SD of mu, is n minus o over 2. I'm kind of running pretty short on time, so maybe what I should do is just kind of move these by quickly. Here's an upper bound for the C of mu function, which depended on those weight diagrams that I talked about and the allowable functions, giving us a sort of a control over what how lambdas could occur, and then we use the final dimension formula and some tricks that Anne and John and I had discovered before. Here's some stuff on support varieties. If you already know what a support variety is, you can skip the first paragraph. And if you don't know what a support variety is, you can still skip the first paragraph, but it probably won't be very meaningful. Some of these support varieties are given by a rank variety, which is this description over here. And we were able to figure out this G minus 1 support variety of delta mu is the skew symmetric n by n matrices of rank n minus o, take the closure of that. And the actual complexity of this thick Katz module delta mu, not the C of mu, but the C of delta mu, is the dimension of that variety, which is an easy linear algebra exercise, n minus 2 minus n choose 2 minus o choose 2. And that put together implied that this projective resolution that we constructed at least has the same rate of growth as the minimal projective resolution, which actually is a very strong statement, to be honest. But here's some stuff that maybe is not worth spending time on, but I'll just maybe point out this second fact here. This really just follows from tricks that VKN already figured out. But this GG0 support variety of delta mu is 0. And that's kind of weird because delta mu is not projected. It's projected if and only if mu is typical. So this is a phenomenon that happens in type 1. And it's the sort of the failure of the support variety theory to detect projectivity. Dan was suggesting 3 weeks ago that we could define the atypicality of the module to be the dimension of this variety. So according to that definition, the atypicality of these thick Katz modules would all be 0. If I can just take a couple more minutes, let me just say this last theorem. We figured out so F is this detecting subalgebra that VKN introduced and Dan talked about 3 weeks ago. The dimension of the support variety relative to its detecting subalgebra and the Z complexity of these thick Katz modules is this number n minus o over 2. So I just want to end by saying some things about questions. What is the correct definition of atypicality of a weight for P of n? In the BKN4 paper, we proved that the dimension of the F support variety and the Z complexity of a Katz module is equal to the atypicality of the weight. So comparing that to this formula here, we are proposing that the atypicality of this weight, or the atypicality of the weight mu, is n minus o over 2. Notice that if mu is typical, that means that the dots are all isolated. So the runs, number of parent or runs of adjacent dots are all length 1. There are n odd runs. They all have length of 1. n minus n over 2 is 0. So at least this gives the right formula for a typical way. And it gives something that you can actually define combinatorially in terms of roots and inner products and stuff too, like it's done for GLMN. So, no idea. No idea. So question 4 is, can we compute the support variety for some other kinds of interesting modules, like a simple module, or even big cat modules? We have no idea how to do that. In GLMN, we really heavily use the duality to get control of these other families of modules. We don't have the duality here, the transpose dual, and so we have no idea how to do that. So that would be really interesting. We don't have cover. Question 3, is there a cover? And of course, question 2, I already mentioned, is this resolution constructed a minimal resolution? I don't think we even have a real guess. We're just not really sure. It's close to minimal, and I think these occurrences of the same indecomposable in 2 successive degrees are very rare. And if you could get those were not supposed to be there. So what can happen is you can have an isomorphism between those 2 things, and then that could just be deleted from the resolution. There are very few of those that would have to be deleted, I think, to give a minimal projective resolution. So I think it's within epsilon to be minimal, but anyway, sorry for going over. Thanks.
So can we generalize this to other types?
Well, I mean, it's already done for GLMN in the VK4 paper. One of the formulas that I didn't have time to talk about is the closed Sorganova associated variety. The dimension of that plus the dimension of the zero variety equaling the complexity is a formula that's known in a lot of cases. What's his name? Jon Kujawa student, Hussein Elter figured that out in some units of type 2 cases where that works for classical module, F module, and simple module. So there's some things that have been done along these lines in other cases. I don't know, this is maybe the most challenging one so far. We have to use partial results, but we still don't even know if this is a minimal.
You mentioned that open conjecture. Proving in general.
They haven't said it's an open conjecture to prove in general for any module type formula, but the sum of them, yeah, that's right. It's known in a lot of cases that the sum of the dimensions of these 2 closed Sorganova associated variety plus our GG0 variety equals the complexity of that module. The rate of growth of dimensions of the minimal projective resolution. And like I said, it's known in quite a few cases for certain families of modules, but we certainly don't know that. The work for these 6 gas modules here, we don't know the 10 gas modules. Thank you.